Uh, look, anyway, so that you'd have to think about how you're going to wear it. And every single personal study I do, it ends up you need a different way of wearing the monitors. And even in that first study, we made that backpack. We made red and green backpacks. We went to the school. We said, we're going to do this study. And all the kids said, we'll never wear that backpack. And we were like, well, why not? And they said, it's red, it's green. We only wear blue and black backpacks. So these little details actually really matter. We had to go back, make new backpacks that were blue and black, and then the study went very well. So here are these examples that you're looking at now that are going around of kind of the recent research grade personal air monitors. The first one is a UPass. It's their second generation. You actually have both their first generation, which only collects a filter, and you have their second generation, which collects a filter and then adds a low-cost PM sensor onto it. Where did that? It's the sensor on sensor. Oh, so they just added this on. They also added electrochemical cells for NOx and VOCs. The NOx does respond. The VOC is useless. And they also have a little CO2 sensor that is also okay as long as you calibrate it in the lab. It has a light sensor, and it has an accelerometer. And that's really key. All personal monitors should have. Guess what? If you're not wearing the monitor and you're sitting somewhere, is it personal monitoring? No. It's not personal monitoring. So you need an objective way. I joined a study once and I added a monitor to somebody's backpack, and they had someone visiting the home every day for a week. And they promised me that their wearing compliance was really high, just based on them visiting the home and seeing that every time they visited the home, the student had the backpack on. I added an accelerometer. They only wore the backpack when the person came to visit. They wore it half an hour a day. So you really need objectively measure. Even better is objectively measure and give them an incentive for wearing it a lot. And we'll look at that in a second. The other monitor that's going around is this Atmo tube. And though we use this in personal, we've also set it up for an indoor monitor. We've used it as an ambient monitor, very flexible monitor. Next slide, please. Do that. So this is the Atmo tube. Its main claim to fame is that it's $150, where that UPass V2 Plus is around $2,600 in the US. It really just has a sensor on PM sensor, and it's the same one as in the UPass, but it has no accelerometer. It doesn't collect a filter for calibration. So you really need to co-locate it with something else. Next slide, please. So I spoke about this calibration. We look at the average sensor response over the whole deployment that we also collect a filter on over the same time. And so you might be walking around and seeing very different sources that have different optical properties and thus different optical response in the sensor. All you get, the mass-weighted average response. But I would argue that's better than not knowing anything. And so this is a good publication for understanding how to do that calibration better. Next slide, please. Can we go back? Can you go back for a second? So one thing is, it's a big deal. The correction factor can vary by a factor of 3 between the 10th and 90th percentiles. So it's not a small correction factor, it's a big correction factor. Next slide, please. So household air pollution, major source. So your exposure over time has really high values for short periods of time and then can go down to very low values. Well, if you're not wearing the device during these periods when you're cooking, because you found that the way of wearing it was uncomfortable, then you're going to be totally missing the exposure. People have studied in detail indoor, the variance next to a fire indoors that's unvented, and it's more than a factor of 10 vertically, and it's more than a factor of 10 with over short distance scales. And that's in an indoor setting where there's some mixing going on, keeping the smoke in the room. In an outdoor setting, you have even where people cook, you have even larger variations. And then it's totally dependent on your behavior and how you interact with the cook fire. Next slide. So the objective way of measuring wear and compliance is looking at an accelerometer, which is just looking at accelerations in 3 different axes, X, Y, and Z. When there's a lot of variation, the unit's being worn. When there's not a lot of variation, the unit's not being worn. It's really simple. Next slide, please. And it matters. So here's results from a household air pollution study up in Contampo with run by the Contampo Health Research Center. And what we have on the x-axis, the mean wear and compliance during waking hours. And what we have on the y-axis is the average 48-hour PM 2.5 concentration. And it's broken down into the 3 different arms of the study. And what you saw is that never plateaued. And we did a lot of statistics on this. It really looked like you really wanted the person to wear it as much as possible. And if you really wanted to know the true exposure to PM 2.5 over 48 hours, you really wanted to be up here, wanted to use this correlation factor that we got to correct the data to be up there. Next slide, please. So here's an example. That was the graph study we just looked at. We continued to follow these students at age 4. We got similar wear and compliance. At age 7, something happened. At the beginning of the study, we had horrible wear and compliance. And we were told that the harness that we used for the pregnancy study, that the women didn't like wearing it because people thought they were pregnant when they weren't. Or maybe people thought they were pregnant and they were, but they didn't want their mother-in-law knowing that they were pregnant yet. And so they weren't wearing the monitor. So we changed the harness. We were still getting bad wear and compliance. Next slide. And so we did 2 things. We paused the study and we did community sensitization. We went to all the communities, talked to them about the importance of the study, gave them the results of the prior study. And we also started this conditional incentive. We gave powdered soap to the mother. If she wore it, we gave a reusable water bottle to the child. And they got that if they wore it on average for more than 10 hours a day over the 48 hours. Next slide, please. So here's the period of bad wear and compliance. I mean, there were some people still doing well, but the median was down by around 5. Here's the pause. We started this conditional incentive. It went zonking up. Next slide, please. Without the conditional incentive and the community sensitization with it, it clearly works, and it doesn't take much of an incentive. Next slide. So what if your personal monitor doesn't have an accelerometer? Well, there's now a data logger that combines both accelerometer and GPS. It's made by Gulf Coasts. It costs about $250 though, but they designed it for me actually. So it'd be great if more people bought it because then they'd get a return on their investment. And this is just a GPS data logger we were using before. One thing to know that the GPS and that UPass UV plus or V2 plus is horrible. It consumes a lot of power. It takes a long time to get a fix. It's not worth using unless you're just some simple tests. So we've always used external data loggers. Next slide. So here's the first case study. And here, this was an exposure study, no health, but this was mandated by the Clean Amendments of 1990. And they wanted to know in urban settings, what were people being exposed to who weren't occupationally working? So we did teenagers. And they wanted to understand what the sources were, where it was coming from. Was it coming from wind? Was it coming from urban sources? Was it coming from indoor sources? Next slide. And so we did the work in LA. We did personal monitoring, but we also, because we didn't have the real time, we had to collect a whole bunch of other samples to make sense of it. We collected inside the home. We collected right outside of the home. We collected central site at their school, and we collected upwind. And we looked at a whole bunch of different parameters. Next slide, please. This is where the kids lived, at least in New York City. So they were out. This is where the school was, and this was our upwind air monitor, where our lab is. Next slide. Notice every kid in this school is wearing a blue and black backpack. Obviously, the red and green wasn't going to cut it. Next slide. So here's one of the things we measured on the filters, cobalt. In yellow, the upwind air monitor. Notice it's the lowest. We had our urban fixed site air monitor. It was much higher. And then we had in pink, the home outdoor. And notice even a lot of variability in that. That's telling us there's lots of local urban sources for the cobalt. Indeed, cobalt comes from the oil that we use a lot for space heating. And so every apartment building could have its own source. Next slide, please. Here's arsenic, totally different, very little spatial variability. Lots of temporal variability still, but upwind, urban, central, home outdoors all look the same. This arsenic comes from coal combustion, primarily. And the coal combustion is primarily a few states away, so several hundred kilometers away. So by the time it gets to New York City, that air is well mixed and everything is the same. This simple idea of variability, looking at spatial and temporal variability, is a very powerful tool. Next slide. We'll skip this for now. And we're going to skip all these. This one. Okay. So personal versus home indoor, home outdoor, urban fixed site, upwind fixed site. For iron, the personal clearly is getting a very different signal than all those ambient air monitors. You're totally missing the exposure that these kids were getting. It took us a long time to figure this out, but we basically tracked it to, they were riding the subway to school, and the subway has really high levels of steel dust because of the subway cars. And so we proved this by collecting a sample that was only in the subway. So this is case study number one of why personal was critical for understanding the exposure to iron, manganese, chromium, and several other metals that are in the subway system. Next slide, please.